In this video, we will talk about how to set up Newton's second laws for oscillation. And we'll talk about 4 different systems: horizontal spring, vertical spring, simple pendulum, and physical pendulum. We'll talk about how to set up Newton's second law for all these oscillations. So for the first one, horizontal spring. So for this setup, there's a horizontal spring, of course. And let's say there's a spring attached to a wall, and the other end of the spring is attached to a mass. Here's the mass, and the mass, its magnitude is m. Now it's on horizontal surface. Now suppose that at this position, the spring's length is the original length of the spring. So let's call this L naught. That's the original length of the spring. And after that, let's say we pull the spring to a new position. Let's say here. Then compared to the original length, now the spring length is longer, and we can say there's a displacement for the spring, or there's a displacement for this mass m. Now for this kind of oscillation problem, we need to set up coordinate system, and the origin of the oscillation is usually set at the original length of the spring. And for some other session, I'm going to talk about the different kind of the origin setup. Okay, but right now, the original length of the spring is the origin of the coordinate system. So here's O, origin O, and we're going to set up a one-dimensional system so that the right side is the positive x-axis, and of course the left side is negative. Now let's compare the original length of the spring with this new position here. Let's call it position x. Okay. Now let's displacement. We can draw delta x to the right side. That represent the spring's displacement or the mass m's displacement. Now there's a Hooke's law that relate the spring force with this displacement. It says that the spring force equals k times delta x. So the spring force is proportional to a constant called k, which is called a spring constant, multiply the displacement of the spring or the mass. Now, because the spring force and also the displacement, they are vectors. So if you want to write this equation as a vector equation, then we need to add a negative sign here. Okay, because in this position here, the spring force is backward, is trying to pull the mass m back to the origin O. So that's the spring force direction. Now, if the spring is compressed, let's draw this situation here. Let's say now we have this diagram. Mass M is here, and then the spring now is compressed. Then the displacement of this object or the spring is delta x is to the left. And the spring force will try to push this mass M back to the origin O. That's why we have this spring force direction to the right. Now, because of that relation, you can see the spring force and the displacement, they're always opposite in directions. And the spring force always points toward the original length of the spring. So that's why such a force is always called a restoring force. Because the spring force will always try to restore the original length of the spring. Okay, so now with that restoring force, if we set up the system, let's say pull it to this position and then let go, the object will do oscillations around this original length of the spring. And because the oscillation is along this position, so we call this equilibrium position. And in this setup, it refers to the origin O as the equilibrium position. Now, that's a general definition for the equilibrium position. It's the position where the restoring force, the net force on the mass M equals 0. So the official definition is that the net force on the mass M equals 0. Because that's our definition of equilibrium from Newton's second law. So the net force need to be 0 at this position here. And that's satisfied by this picture because we know at the origin the displacement is 0. So that's why the restoring force is also 0. So the net force on the mass M is 0 here. Okay, so now with this Hooke's law, with the restoring force represented by this equation here, then we can set up a differential equation according to Newton's second law. So now let's say, because in this diagram here, delta x is x. Alright, so that's why we can rewrite it as this equation. So according to Newton's second law, the net force in this x direction equals the spring force equals negative kx times I hat. And that equals max according to Newton's second law for this mass M. Now we know ax is given by the second derivative of the position x with respect to time, and then times I hat. Okay. Now in the future, since we're talking about 1D motion for oscillations, so we can neglect the I hat, the unit vector along the x-axis. We can neglect them, and we can simply just look at the following differential equation. So negative kx equals mass times the second derivative of the position vector. And then we will try to rewrite this as some standard differential equation. So first we divide both sides by m. And then we move the left side, the left term to the right side. So we get its differential equation. equals 0. And we're going to define a parameter called omega equals square root k over m. Okay, now with that definition, this equation becomes the second derivative of position with respect to time plus omega squared times x equals 0. Okay, and this equation is called the standard differential equation for simple harmonic oscillation or simple harmonic motion. And we'll talk about how to solve for the solutions of this differential equation in the next video. Okay, so now we're going to talk about some other systems that also give us exactly the same equation like this one. Now think about the vertical spring system. Now, before I talk about this vertical spring system, let's remind ourselves of what we did here for the horizontal spring system. So first, we figure out the origin of the coordinate system O, and we call that equilibrium position. And at that position, the net force acting on the mass m equals 0. And that's very important because we know the oscillation of the object of the mass m is along this position. So that's why we can define it as the origin, and then the coordinate of this object m can act as this the variable x in the differential equation, because now the net force is directly given by this position x in this formula, negative kx. So we're going to do the same thing for vertical spring system. And let's try to first think about the equilibrium position. Equilibrium position for the vertical spring, and we're going to say that we need to find the net force equals 0 position, and then we'll set that position as the equilibrium position. Okay, so now here's the several instances of the vertical spring. So now let's say the spring's original length is this length. L0. Okay. So now nothing is hanging on the spring. Now on this position, let's put on a mass. And then we'll let the spring stretch to this new position due to the mass m, due to gravity mg, stretch to this new position and then stop. Okay. Now I'm going to say that this position is the equilibrium position for the vertical spring, not the original length of the spring, not this position, but here, this position here. Okay, so I'm going to set the origin here, and then I will explain why we do this. So that's the origin O level, and then we can say the one-dimensional x-axis is downward. Okay. So why this position is called the equilibrium position? That's because if we draw the free body diagram for the mass m, then there's a spring force F spring pointing up and gravity pointing downward. And these two forces, because the object M stops here, so these two forces cancel each other at this position. So that's why we say the net force equals 0 at this position. Okay, so now anything extra, let's say if we pull the spring now to a new position here, we pull it down and then let go. Then this new position has coordinate x for the mass m. We can also say the spring now has a coordinate x. And the force acting on the mass here now is, the spring force now is bigger than the previous one. That's the restoring force. Gravity is still the same. Still mg. So now if I calculate the net force here, it equals the summation of the spring force plus the gravity. So we get, for the spring force, I get, let's call this spring force F spring naught. Okay, so you're going to get negative F spring naught, and then plus an additional K times X. Okay, because based on the origin O, now there's an additional stretch of the spring by length X, so that's why we obtain this additional force, negative Kx. And then plus the gravity mg. Gravity is positive because it's in the same direction as the x-axis. Now that is the net force at this new position x, equals, according to Newton's second law, max. Now since we know from this second position we have net force equals 0, and that means that negative F spring naught plus gravity equals 0. So we can cancel out these two terms here. Their summation equals 0 due to the second picture here. So that's why we get negative Kx equals max, which is the second derivative of the position x. Okay, so now we get exactly the same equation as before for the horizontal spring. So the equation looks exactly the same, where the omega is defined as the square root of k over m. Okay, so that means that whether the spring is horizontal or vertical, it doesn't matter. The only thing that changes from a horizontal spring to a vertical spring is the origin O, is the equilibrium position change. And we need to offset the gravity by an additional length of the spring from its original length. And then the equilibrium position can be found out this way. Okay, that's our second system, and then we get exactly the same differential equation as the first system, the horizontal spring, same equation as this one. Now we're going to talk about another system, simple pendulum. Let me first draw the diagram for the simple pendulum system. Now the dashed line is vertical, and then we're looking at a string with length L, and then there's one end is tied to a small ball, the other end tied to the ceiling, and then if we move this ball away from the vertical, then and then let go, then the ball will start to oscillation around this dashed line. Okay, now clearly from the picture, we know it's going to oscillate along this line. So we can say the vertical line here is the origin O. That's the equilibrium position. But now think about what quantity is exactly doing the oscillation. It's not the one-dimensional like linear position x as we know for the spring system. So it'll be something else. Now we notice that this angle here, let's call it a theta angle. This angle is changing from this right side value to the left side value, and then back and forth, oscillate back and forth. So we're thinking about using this angle as the replacement of the position x. So instead of using position x, now we transition to using the angular position. So previously it's linear position vector x. So now it's angular position theta. Okay, so now the linear Newton's second law we know is net force equals ma. Okay, now for the angular kinematics, we remember that we need to talk about net torque. Okay, so net torque equals I times alpha. Okay, that's Newton's second law in terms of angular oscillations. So we'll try to figure out what's the net torque due to a displacement theta, and then we'll write down the moment of inertia for this mass m rotating around this center here. So here we call O. Okay, so now we realize that the O that we try to set up is not here, right? It's here. Rotation axis O, and that's the equilibrium position. Okay, where we have net torque equals 0. So equilibrium position refers to the net torque equals 0 position. Okay, so now let's say we are at angle theta. Then how do we figure out the torque here? We need to do the free body diagram first. Now the string here is going to pull up the mass m in this direction, and that's tension T. Now the gravity is in the vertical downward direction. That's mg is gravity. And then we know rotation axis is here. That's axis O. So we need to figure out the torque due to these two forces with respect to the rotation axis O. Now torque due to the tension force equals 0 because the tension force goes right through the rotation axis O. So the level arm for the tension force equals 0 here. Now the torque due to gravity is non-zero. So let's figure out how we can calculate its level arm. So we need to extend the line of action, the gravity's line. It's this vertical line, right? And then the level arm is given by drawing a vertical line from the rotation axis toward the line of action. And that distance, the shortest distance from rotation axis O to the line of action is called the level arm. Let's call it R here. Okay, so the torque of gravity is R times mg, level arm times the force. Now, how about direction? The direction here is using right hand rule. So in this direction, the torque here is going to pull down the object in the clockwise rotation. So we're going to rotate this M in a clockwise direction. So that direction is defined as negative direction. So let me write something here. So clockwise torque is negative. And counterclockwise torque is positive. And that definition also applies to angle. So let's say we're looking at a clockwise angle, then it's negative. And counterclockwise angle is positive. So let's look at some examples of this angle here. Since we know the torque already, for this mass here, the gravity is pulled it down, so it's going to rotate in the clockwise direction. So that's why it's negative here. But how about angle? Now, right now the angle is here, and starting from the dashed line, we need to rotate along this counterclockwise direction to this angle of theta. So that's why this angle is positive. Now, if instead the object is on the left side, so we draw a dashed line, and that's the mass m. Now, from the equilibrium position, we need to rotate clockwise to this angle. Then this angle is negative. And then how about the torque here? The torque due to the gravity. Now gravity is here, pulling it down. Tension force again has no torque. And gravity is pulling this object down in this counterclockwise direction. Right? So that's why this direction is positive. The torque in this case is positive. And the previous torque at this position is pulling down the object this way in a clockwise direction. So that's why it's negative. So now we see the correspondence here. So if the to summarize this picture, so if the theta here is positive, then the torque due to gravity is negative. And if the angle is negative, then torque G is positive. So that's why we call the torque here due to gravity as restalling torque. Because the effect of this torque due to gravity is always trying to pull the object back to the equilibrium position. The vertical line here is the equilibrium position. So that's why it's called a restalling torque. And that's why we naturally have this negative sign here relating the torque with the position theta. We'll see more clearly this relation later on. Okay, so let's rewrite this R here so that we can see that relation, torque theta and torque tau G and theta relation. So R is given by the length L times this sine theta angle. So let's write this down. So mg, let's copy that. R now equals L sine theta. Okay, and then equals tau g. Okay, so now we see clearly if theta is positive, then sine theta is negative. And due to this negative sign, the torque now is positive. And if theta is negative, sine theta is negative. Sorry, previous one, sine theta is positive. And then the torque here now is positive. Theta negative, tau g positive. Theta positive, tau g negative, yeah. And that's the relation we were talking about. That's why torque due to gravity is called a restoring torque. Okay, so now think about under such a restoring torque, what kind of differential equation we get for the mass m's rotation. Now here's the Newton's second law for rotation. So we need one more ingredient here, the torque, the moment of inertia of this mass m. Now rotation here is around the point O, which has a distance L to the mass m. So the moment of inertia is m times L squared. Then we can say, according to Newton's second law, for rotation, we have the net torque equals torque due to gravity equals negative mgl sine theta equals I alpha. Now alpha is the second derivative of the angle theta. So let's replace it by d theta dt squared. Then we get this equation here, and then now the differential equation is nonlinear. So let me first write this down. So second derivative of angle theta plus mgl over I sine theta equals 0. So that's non-linear differential equation. And we don't have an analytic solution to such a differential equation. So that's why we want to think about some approximation here. So now let's say if the theta angle is small, think about what will happen here. So sine theta, we can do a Taylor expansion along the theta equals 0 point. And there we have sine theta equals theta for the first linear term. And if we do that replacement, then we get second derivative of theta plus omega squared times theta equals 0. And the omega here is given by square root mgl over I over moment of inertia. Now this equation is exactly the same as the previous spring system, with only the replacement of x by theta. Otherwise, the equation looks exactly the same. So that's again the standard differential equation for simple harmonic motion. Of course, the angular, this omega here is called the angular frequency. The angular frequency's definition now is different. All right, so let's talk about the last system, the physical pendulum. Let's talk about how to set up the system's dynamic equation. Now, again, we need a vertical line, which we call equilibrium position. And then the object here is some kind of arbitrary shape. arbitrary shaped object, and then we're hanging this object with the point O, which we call rotation axis. And for this arbitrary object, let's say its center of mass is here. Okay, so now we use some concept in the in chapter 10 on the literary bodies definition. There we define center of mass. So now let's say the distance from rotation axis O to the center of mass is L. And then the object here now is displaced by this angle theta from the equilibrium position. So again, here's the equilibrium position. Okay. Now we know the gravity is acting on this object. And at this hanging point, of course, there's a normal force acting on the object. But the torque due to the normal force must be zero, right, because it goes through the rotation axis. And torque due to gravity, now let's see what can we get from here. We need to extend the gravity's line. Again, that's the line of action. And draw a vertical line from rotation axis toward this dashed line. And that gives us distance r from O to this dashed line. And r gives us the level arm. So that's why it's r times mg. And the effect of gravity now is pulling down the object, so the object will rotate this way in the clockwise direction. So that's why we need to add a negative sign here. That's negative torque. And that gives us the torque that we need for the differential equation. And just like the previous simple pendulum case, we have this torque equals negative mgl sine theta. Okay, so we get exactly the same equation as before, with r given by L sine theta. Then we can set up the Newton's second law. The net torque equals torque of gravity equals negative mgl sine theta equals I alpha. And alpha is the second derivative of the angle theta. And then we get exactly the same equation by the small angle approximation. So under the small theta approximation, we have sine theta approximately theta. And then omega is then given by square root mgl over I. Okay, given by that. All right, so that gives us the same standard differential equation we need to solve. And we'll talk about this solution in the next video. Okay, that's all for this video. Thanks for watching. In this video, we'll talk about energies involved in a simple harmonic motion. Let's take spring as an example. Now for springs and also mass system, the spring constant is K for the spring, and the mass is M for the block that is oscillating. And let's say it's on a horizontal surface, okay, oscillating on a horizontal surface, and the equilibrium position is here. It's called O. The x-axis is like this to the right. So I'll set up. Okay, so right now the mass M, let's say it has velocity v going left in this direction. So now I talk about the energies involved in such a system, the spring, mass, system. So the mass is moving with velocity v, then of course it has kinetic energy K equals 1/2 mv squared. Now with respect to the equilibrium position, the mass M has position x. Now remember in the potential energy chapter, we talk about the potential energy for a spring, and we said that if the spring is stretched by let's say length x with respect to its original length, or the equilibrium position in our case here, then the potential energy is given by 1/2 kx squared. Okay, so that's the U here. Then we can add up the total energy here, K and U, and then we call that total energy of the spring mass system. We call it E. Total energy here is actually mechanical energy. So we use E here to represent the total mechanical energy, equals K plus U. And that equals 1/2 mv squared plus 1/2 kx squared. Now, since we're considering smooth surface, so let's know kinetic friction involved in the oscillation of this mass M. So no friction force doing work here. And of course in the vertical direction there's a normal force supporting the mass M, and gravity here is in the downward direction, but they do not affect the total energy of the system. The normal force, which is non-conservative force, does not do any work. So that's why the total energy here should be a constant. So that's called the energy conservation for simple harmonic motion for this spring mass system. We can actually check this equation. So let's see. We know x equals a cosine omega t plus phi naught. That's our general solution to the differential equation that we talked about in the previous video. And the velocity is negative omega a sine omega t plus phi naught. Okay, so now let's see what kind of equation, what kind of result we get here if I sum up these two terms. So the total energy now equals 1/2 mv squared, so that's 1/2 m. V squared is this term, right? So we get omega squared a squared sine squared omega t plus phi naught. And then plus 1/2 k times x squared. X squared is this term squared, so a squared times cosine squared omega t plus phi naught. Now what do we get here? Remember, omega is square root k over m. So omega squared is k over m. Now if I plug this in this equation here to place omega squared, let's see what we get. So 1/2 m times k over m squared. Sorry, there's no square. K over m. And then multiply a squared. Okay? And then there's a sine function squared. Plus 1/2 k a squared cosine squared. Now let's see, the coefficient of sine square and cosine square, they look exactly the same because these two mass cancel out. So we have 1/2 ka squared for both terms. So that's why we can pull out this common factor and then group them, the remaining terms together. So we have sine squared plus cosine squared. Okay, and that equals 1 because that's the identity. 1 here for this sine square plus cosine square. So in the end, we get 1/2 ka squared. Okay, so now we know the constant now, right? The constant in the spring mass system in the oscillation is given by 1/2 ka squared. Okay, and let's think more about this total energy. So the total energy, because it's conserved, so at any position during the oscillation, the energy is always the same, including the maximum displacement position. So let's say the object now is here. Now this distance to the equilibrium position is a. That's our definition of the amplitude. And that will correspond to this point because the velocity equals 0 here, because that's the maximum displacement. So the mass m cannot go further away because the velocity has to be 0. So that's why the total energy here is given by the potential energy of the system, which is 1/2 ka squared. Okay, so now to illustrate that, I want to start a new page and then talk about some special points of simple harmonic motion. Now the first special point I already point out is x equals plus or minus a. Now at these two positions, the kinetic energy of the system equals 0. That's no speed. And potential energy is 1/2 ka squared. Therefore, the total energy of the system is k plus u equals 1/2 ka squared. Now the second special point is when x equals 0. So that's the equilibrium position. Now at this point, now we know u equals 0 instead, because there's no potential energy. 1/2 k x squared equals 0. Now the k here, we know is 1/2 mv max squared. Okay, so when the object passing the mass m passing the equilibrium position, its velocity is maximum. So the total energy of the system is k plus u equals 1/2 mv max squared. And that should be equal to the total energy of the system at x equals plus or minus a. Those maximum maximum displacement positions. So we get this equation here. So V max squared equals K over M times A squared. Now K over M is omega squared times A squared. So V max equals omega A, okay, equals the amplitude times angular frequency. Now this result is actually implied in the velocities equation. So velocity equals negative omega A sine omega t plus phi naught. So we can say the velocity here is also doing oscillations. The value of this velocity v is some numerical value that is oscillating along an equilibrium position, and its oscillation amplitude is here. So that's the amplitude of velocity's oscillation. The amplitude means maximum value, so that's V max equals omega A. Okay, so that's the same as this understanding from the energy point of view, and now they're all connected. Now at some arbitrary position x and v, then we have both terms. So you can say 1/2 mv squared plus 1/2 kx squared. Okay, so now that is a constant, which is 1/2 ka squared. Okay, so sometimes we can relate some arbitrary positions energy to the special positions total energy. Okay, now reflected in diagram, let's draw the energy diagram. For the simple harmonic motion. Then we know so let's say these vertical axes represent energies, and horizontal axis is the position x. Now for the equilibrium position O, that's the origin O here, there's no potential energy U. So potential energy must be, use a different color here, must be 0 here, going through here. And at point positive A and negative A, they're both maximum. So that's why we have this parabolic curve. Between positive and negative A, and in general, U here is 1/2 kx squared for some arbitrary x. Now how about k here? K is 1/2 mv squared, and we know k is also given by total energy minus U. Total energy is 1/2 ka squared minus 1/2 kx squared. So for each, because k here is constant, E here is a constant, so we can first draw a horizontal line to represent this total energy E. Okay, E equals 1/2 ka squared equals a constant. So the difference between E and E and U is k. So now if I pick this particular point, this x here, then the kinetic energy is the remaining length here. So from here to there, that's k. And previously the U is here. So if you draw a line to the left side, that's U, and k is this remaining energy of the system. It's this length here. Okay, so that's the representation of the energy using diagram. That's for the spring system. So now let's briefly talk about the simple pendulum system. Its energy. So there's a string with length L, and then there's a mass M attached to the string, and right now the angle is theta. Okay. All right. So now let's say because write down the kinetic energy is easier. So K is 1/2 m v squared, right? And then let's say right now the velocity, let's say at this instant is v. Okay. Now we need to write down the potential energy due to gravity. Now to do that, I need some reference point. And let's say when the mass swing to the bottom here, and we're going to set that as the zero energy level. So the y-axis is upward. So the potential energy at this level equals 0. Okay. Now at this arbitrary position, its height, okay, with respect to the lowest point is this h here, and h is given by the length L here for the string times cosine theta. And then we have L minus that. Okay, so let me rewrite this equation. I forgot. I need to do the subtraction. So it's L minus L cosine theta. Okay, so that's the height h. So if I write down the energy, the potential energy will be mgh equals mgl 1 minus cosine theta. So the total energy, mechanical energy of the system is K plus U, and it must be conserved here, equals a constant, right? But how do I get that constant? Just like in the spring case, we have some constant, 1/2 K times A squared, right? So can we have some similar result here? Okay, so if we think about, let's say, the maximum angle, so the solution of theta is that theta is theta naught, which is the maximum angle or the amplitude of the oscillation. Then we have cosine here, omega t plus phi naught, just like in the spring case. So now can we use this theta naught here to represent the energy? That would be the question. So we're thinking about, let's say right now, the object is at the maximum position. Theta naught. Now this height would be the maximum height, right? So we write down that maximum height equals L minus L cosine theta naught. Okay, so now we assume that the theta naught is small. Then cosine theta naught can be expanded using this formula here. It's the Taylor expansion in math, and we're keeping the second order here. So we get L 1 minus cosine, right? So 1 minus cosine becomes 1 minus 1 plus 1/2 theta naught squared. So we get 1/2 L theta naught squared here. So that's why the energy at the total energy at the theta naught position is given by just the potential energy at this location, because there's no speed for the mass m. So we're going to get mgh naught equals 1/2 mgl theta naught squared. So this 1/2 mgl is like 1/2 k. So this one is like k in a spring system. So we also have a quadratic potential energy for the system, and the total energy of the system is given by 1/2 mgl theta naught squared. Okay, and the other discussions are the same as the spring system. Okay, so that's the energy for simple harmonic motions, their relations. Thanks for watching.